In this video, we are going to go over section 4.2, second derivatives and graphs. In this section, we are going to continue to analyze the function f, the graph, by using the second derivative test. So I'm going to be kind of referencing back to the first derivative test as well, because in order to have a second derivative, we must take first derivative. So quickly recalling in section 4.1, we learned that first derivative, it gives you information about the original graph in terms of decreasing function, increasing function. Also, we learn about the critical value, and also those critical value can be local mean, local max, or neither. Now, in second derivative, it also tells you a couple more information about function f of x. So let's define couple terms and then theorem to use to get to know the information. And then I'm going to kind of give you a summary of the difference between the first derivative test and second derivative test. And then how we can use to graph that. In 4.4, it will be basically whole summary of section 4.1 and 4.2. Okay, so you have to know the difference between the two derivatives and then what information you can get from first versus second derivative. So second derivative tells you concavity of the original graph. What is the concavity? The graph of function f, the original function, is concave up on interval a comma b if the first derivative is increasing, and then vice versa. We call it concave downward if the first derivative is decreasing. So concavity is just the shape of a graph. So we have two types of graph. This is concave upward, like a parabola, and this is a concave downward. This is a concave up and then concave down. So when we know that it's a concave upward graph, then we are going to draw our function f in kind of U shape. Okay, so how do we find out the concavity mathematically, algebraically? We are going to basically set second derivative greater than 0. And if the second derivative is greater than 0, then you know two information. F prime, the first derivative part, is increasing, and you know the original graph information. F is a concave downward. If your second derivative is negative value, f prime, it tells you two information, is decreasing, and graph of f is concave down. So two information. Second derivative tells you something about first derivative, whether increasing, decreasing. Also the original graph, whether concave up, concave down. Inflection point is very similar concept of critical value. Recall back in section 4.1 when we talk about the critical value, we set the first derivative equal to 0 or find out where where the first derivative does not exist. Same thing. Inflection point, instead of first derivative, we are going to set second derivative equal to 0 or where second derivative does not exist. We call that inflection point. So here's the general strategy so far using 4.1 and 4.2 of how to graph the original function. Step 1, analyze f of x, which means we want to know the domain and the intercept to get the accurate point. Use the first derivative, which is section 4.1. This is section 4.1, and this is section 4.2. Using the first derivative, you're going to partition the number and find the critical value and determine local extrema, whether it changes from negative to positive or positive to negative. Step 3, take the second derivative, same thing, use the inflection points to partition the number and decide the concavity. So you can see kind of like comparison, first derivative, we partition to get information about local extrema. Second derivative, we partition to determine the concavity. And then we are going to use that to sketch the curve. So this is the first version because in 4.4 we have the full version. So this is the simplified version. So that's a lot of information, and you can often get confused with which one is which, first derivative, second derivative. So on the next page, I'm going to summarize nicely into a whole page so you can see the comparison side by side. This is going to be really working out nicely, especially if you start going into a graph, okay? Because you have to know the difference between first and the second derivative. So let's start with the first derivative test. So for first derivative test, what we did is we found out the first derivative if it's, and this is section 4.1, so you can reference back by looking at the previous video. This is great. If the first derivative is greater than 0, then we know information about original graph is increasing function. Vice versa, if the first derivative is less than 0, we know that f of x is a decreasing function. Furthermore, we set f of x equal to 0 or f prime of x does not exist to find a possible critical value. Now these critical value is used to, so we use critical value to partition number line, remember? And then we use the test number to see which one is a positive and negative, right? To determine local extrema. To determine local extrema. So in other words, if we had a first derivative value using the test number going from negative to positive sign, then we call that point, that critical value, local mean. And then if we got positive to negative, then we have local max. And there is a, and then I'll note if no sign change, then critical value is neither local mean or max, correct? So that's what we did in section 4.1. Now, second derivative test tells you a lot of information as well. This is what we are learning in this section. Now, going back here, if second derivative is positive, so I'm referencing kind of like this case, but we are having a second derivative positive, then you are given two information. First derivative is an increasing function, and then f is concave down, concave upward. So you're gonna have f prime of x increasing. Also, you know that f of x is concave up. Okay. Makes sense. You took the second derivative, so you know two information. You only took first derivative here, you are only given one information. So let's write the other one. If it's a negative, then my first derivative function is decreasing, and then f of x is concave down. Okay, so concave up, concave down shape. Concave up, concave down. Okay. What else? Just like critical value, we have second derivative, you use inflection point. Inflection point is when second derivative is equal to 0 or does not exist. So it's similar concept as critical value in first derivative. If second derivative is equal to 0 or does not exist, We call that point inflection point. Then we really do not have a term for local minimum inflection or local maximum. As long as there's a sign change from negative to positive, concave down to up, or concave up to down, we call that inflection point. If no sign change, we don't have inflection point. So if F double prime changes from concave down to concave up, or positive to negative sign changes, concave up to concave down, these are my inflection point. And similar thing, if no sign change, then the point is not considered inflection point. Okay, so this is a nice summary right over here. And I'm going to keep referencing back to this page because it nicely summarizes into one nice page. So let's jump right onto our first question, practicing finding concave up, concave down, and then inflection point. So that's this part over here, right over here. So I'm going to find second derivative, partition the number with the inflection point to see where it's a positive and where it's negative. If it's a positive, concave up, negative, concave down. So let's do that. So part A, let's take the second derivative. So these all deal with the second derivative. So look for the keyword concavity, second derivative, local extrema, first derivative. Okay, so let's start with part A. First derivative, it's a polynomial, so it's a very easy term by term. So 9x squared minus 36x plus 4. And then second derivative, I'm going to have 18x minus 36. Now, let's set it equal to 0, or where it does not exist. These are the number that could be my possible inflection points, and then use those number to partition my number line. Now I know this is a linear line, so it will exist everywhere. Domain is all real, so I'm not having any value from the second case, only first scenario. So 18x minus 36 equal to 0. At 36, I'm gonna have 18x equal 36, and I'm going to have x is equal to 2. So this is the one that I'm going to be partition the number line. So create a number line. Here's my x equal to my possible inflection point. And then remember, we got that from the second derivatives. So we have two regions to check for. Again, when we check the test number is anything that is in that region. So good test point for first region will be 0. Good test number, anything past 2 will work, 3 will work, 4 will work, 5 will work, doesn't matter. So you pick the number that you like. So the first one, the test number I'm going to be using will be x equal to 0. And then the second region, I'm going to have, let me just put it a little bit down. Test number, I'll just use 4. Okay, where do we plug it in? We have to plug it in into second derivative because that's the concavity. Don't plug it into original. Don't plug it into first one. We are dealing with the concavity. I want to know where second derivative is positive or negative. So we plug it in into a second derivative. So Second derivative is right over here. So I have f double prime of 0. So that's 18 times 0 minus 36. I get negative 36. So that means I have a negative. And then f double prime 2, that's 18 times, I meant 4. We do not want to use 2 because that's the partitioning number. My bad. 4 minus 36. So that's gonna be 72 minus 36. I get positive 36. So we have f double prime negative. So negative. So that means I have concave down. So I'm having a concave down, concave up. Because we have a sign change, this is going to be my inflection point. So that's it. That's very simple. So let's go ahead and then answer and then write out our final answer nicely. So part A, where is it concave up? Right over here. So that interval is 2 to infinity. Part B, concave down negative infinity to 2, because we do have a concavity change, x equal 2 is my point of inflection. And then because it's an inflection point, we can actually get an ordered pair. So just like when you find the local min, local max, we use the number, plug it into the original function. So let's plug it in. So that is 3 times 2 cubed minus, I ran out of space. Okay, 18 2 squared plus 4 times 2 minus 10. So the first one, 8 times 3, 24 minus 18 times 4 is 72 plus 8 minus 10. So 24 minus 72 plus 8 minus 10 will give me negative 50. So my order pair is 2, comma, negative 50. That will be my inflection point. Okay, so very similar to our first section. Instead, we just deal with the second derivative. So let's do one more exercise. This time, let's do something other than a polynomial. So let's take a look at exponential function. Okay, same thing, we will be looking for concavity up, concave down, inflection point, exact same thing, except we are dealing with a different function. So I'm gonna do exact same thing. Find the second derivative, find where it's 0 or does not exist to find the possible inflection point, create this number to partition the number line, check using the test number to see where it's a positive and negative. So let's start with taking the first derivative. Part A, first derivative, that's 8 times e to the x, so that's 8 times e to the x. Second one is a chain rule because of 2x, so 2 comes down. So we have 2 times e to the 2x. That's my first derivative. Second derivative, I'm going to take derivative one more time. This one is still 8e to the x. Here, you have another 2 coming from this chain rule. With this 2 makes it 4e to the 2x. Okay. We know, so there are two possible ways you can find the inflection point. Double prime equal to 0, and then double prime where it does not exist. E function domain is all real, so we do not have to worry about not existing. So only case that it's coming from the coming is the first case where second derivative equals 0. So let's set that equal to 0. 8 e to the x minus 4 e to the 2x equal to 0, and solve for x. So I'm going to be looking at this. I noticed that there's a GCF for e to the x, so let's factor that. Then I'm gonna have 2 minus 2 e to the x. By zero product property, I'm gonna set each factor equal to 0. Solve for x. This one, you know that anything raised to the e, I'm gonna get a positive, and then there's no way that I'm gonna get a 0. So this one, we throw it away. There's no x value that will give you equal to 0. Here, let's add 2 to the ex, both sides. 2 is equal to 2 to the ex divided by 2. And then we have hold on. Oh, I went too quickly here and I found a mistake. When I factor out right over here 4 e to the x, I should have just e to the x, not 2. My mistake. So when you distribute it, you get back you get negative 4 e to the x. So let me actually redo the problem. Two minus e to the x equals 0. That's add e to the x. I'm going to have 2 equal to e to the x. This is solvable. I could find a number that works. Here, this is an exponential function. X is on the exponent. So the only way that I can bring down the power is apply ln for both sides. So if I apply the ln, then I'm going to have ln of 2, and then ln of e to the x by the property, because ln is a base e. This cancel out, so x is equal to ln 2. So we do have a x value. That number right over here, I'm going to use it to partition the number line. Could be possible inflection point if there's a concavity change. So let's set up ln 2, and this is the second derivative. We have region 1, region 2. Now, I'm just going to change ln 2 into a decimal to get a sense of what the number is. So ln 2 popping into the calculator, I get this is approximately 0.69. So for the test number for the region 1, I can use a 0. That's an easy one. Number 2, test number. For that, anything that is bigger than 0.69 works. So I'm just going to pick a random number, 2. Use it and plug it back to the second derivative. Second derivative function is right over here, this one. Let's start with the number 1. So f double prime of 0, that's 8 e to the 0 minus 4 e to the 2 times 0. So anything to the 0 power is 1. So first term is 8. This is 4 e to the 0. So I have 8 minus 4, which is equal to positive 4. So I have a positive here. If I plug it in 2, I have 8 e to the second power minus 4 e to the 2 times 2 will be 4. So popping into the calculator, I get negative 50.08. You can get a decimal number, so that's a negative. So my final answer, this is concave up, concave down. Because we have a change of concavity, this is my inflection point. Okay, so now let's use this one to write down our final answer. I'll put it right over here. Let's make it resize, smaller. Put it right over here. Part A. Concave up right over here. So that means negative infinity all the way up to negative infinity to ln2, not included. Okay, just double checking with my work on the side, so it looks good. I got the same answer. Concave down, I have this part, ln2 all the way up to infinity. Inflection point is happening at when ln of 2. So to get the order pair, I would plug it in into the original equation. So 8e to the ln 2 minus e times 2 to the ln 2. And then popping that right onto the calculator. I'm gonna do that. This will be 8 minus e raise it to ln 2 minus e raise it to 2 times ln 2. So exactly 2. So ln 2 comma 2 will be my inflection point. Okay. All right. Let's move on to the last problem. Last problem, I selected one of your homework problem, number 13. And that's kind of like everything that we talked about so far, but Matt organized it in a little bit different way. So let's take a look at this. I'm going to zoom in a little bit to have a better view. Use the graph f prime of x. So you're given, this is not an original function. This is a graph of derivative function, first derivative. To discuss the graph of original, organize your conclusion in a table and sketch possible y equals f of x. All right, so let's take a look at this one. I'm going to zoom in a little bit. In fact, let's take a screenshot. I'm gonna zoom in. Okay, let's just try one more time. It's a little blurry. Take a screenshot, save image, and I'll just put it kind of like a little bit bigger view. Okay, I'm gonna zoom in a little bit. Okay, so if you look at this one, you have kind of like important points here. Remember, this is f prime of x, the derivative function. We have 1, 2, 3, 4. This point is kind of important. this point, and then this point. So you can kind of partition this way, which is what they did. This part over here is negative infinity to negative 4, which is this one here. And then x equal negative 4 is this point here. And then we have a another region right over here going from negative 4 to 0. This region, this part right over here. And we have this partition part right here. That's 0 to 4. And this last part, which is x equals greater than 4 to infinity. So let's analyze. Notice that all these graphs, right, are above x-axis. So that means f prime of x is greater than 0. Everything is above x-axis, positive value, right? So, and then let's interpret this one just like when we did it in first derivative. This is a decreasing here because it's going down. And then we have an increasing part, and then decreasing part, and then up to the increasing part. These are the things that I want you to note, right? So you have, now let's start fill in the blank. First part, you have f prime, two things, positive, but decreasing and decreasing. I'm gonna skip this one for now because that's a point. This region right over here, the second interval between negative 4 to 0, which is this one here, I have still positive, right? This means all positive. So they all begin positive number. And then this time, we have a increasing. Let's look at this region, 0 to 4. Positive again, always positive, and then decreasing. And lastly, we have this one, positive and increasing. To check and see if these are our local mean or local max, you need to have the sign change, right? So take a look at this. We have a decrease. So this part over here, we have first derivative decreasing to increasing. What is decreasing to increasing mean? Decreasing to increasing, we have a local mean. Right? First derivative going from decreasing to increasing, we have a local mean. So this point is local mean. Just going to use different color. Local mean. And this does look like our minimum point, smallest point, lowest point on the graph. Same thing here. You can kind of see that this is also going to be local mean, and then this is local max. But let's check. Increasing to decreasing. Change in the concavitive. Increasing to decreasing. We have local max. So that point over here will be local max. Okay. And then here we have decreasing to increasing. So it's just like this one over here. So this will be local mean. Okay. So that's the first column. Now let's look at f of x. So I'm going to be erasing to create more space here. Just erase a little bit. So this part over here, that's going to be dealing with a original function. So let's take a look at our summary over here. This is where it comes handy. You have f of prime. So if I'm looking at the first row, I'll copy down over here. The first column right over here tells me f prime is positive and decreasing. So I'm going to be copying this and then paste it over here to see. Oh. Okay, let me copy it again. Only handwriting. Paste it over here and match up. So we have a f of prime is positive. In other words, that means this part is greater than 0. And then we have f prime decreasing. And we want to know information about f of x. So take a look. When f prime is a positive, then we have a increasing function. So this tells me f is increasing. This means f original function is increasing. And then if you have f prime decreasing, right over here, f prime decreasing, original graph is concave down. So that's how I know the information about our function, about original graph. So I'm gonna copy this one so that we don't forget. Copy and then paste it over here. So this first column will be increasing and concave down. Okay, so that's how you know go backward. So let's skip this one about inflection point. So now you have a positive and increasing. So positive will tell me increasing. And then increasing will be the opposite of concave down. So concave up. Okay. Positive, so everything will be increasing because we have all positive. Increasing and decreasing means I have a concave down. Lastly, positive means increasing. Original function is increasing and original graph is concave up. Now, same thing. We looked at the sign change. Decrease to positive makes a local minimum. We have concave down and up. There's a change of concavity. So this point is an inflection point. We change from up to down. So this indeed make inflection point. We go from down to up, change concavity, so this is inflection point. Okay? All right, so that completes all the information about our original function f of x. Now, part B is asking you to sketch f of x. So I'm going to be using this entire column right over here to create a graph. So let's do that. let's kind of create a grid and partition it 1, 2, 3, 4. I'll just use a imaginary line. Negative 4 to 0, and then 1, 2, 3, 4, this one. And then this is region 1, 2, 3, 4. And this is information about 1, 2, 3, 4. So I kind of like to sketch it and match my graph with the option. So first one, you have an increasing and concave down. So concave down generally means this shape, but you are not gonna have an entire concave down part. You only have an increasing and then concave down. So if you read through left to right, the function is increasing and concave down. So this is the only parts that we are going to be using in the first region. So I need to have something like this one going on here, okay, on region 1. So I'll leave it little, I'll just kind of like put it over here. This is the only part that I will be using. Let me highlight it. This part only. Okay, this part. Number 2 is right over here, increasing concave up, increasing and concave up. What is that shape? Well, concave up generally is opening up parabola, and then you have increasing. Increasing means going up. This is decreasing, getting smaller, and then increasing. So this is the only part that I'm using. So I should have something like this part. Okay, so we have this one and then this one. Number 3, we have increasing and concave up. Number 3 is concave down. So we have, this is the part that we will be using. This is the part that we will be using. Increasing and then concave down. So concave down is this one, but increasing will be only this part. So I'm gonna have kind of like this one again. Number 4, we have an increasing and then concave up. So the shape that we are looking at, this is a concave up generally, but only the increasing part, this one. So I'm gonna have this one. So this is how I kind of sketch it. This one is from region 1. So this part over here, I should have something like this. And then region 2 should have something like this here. I'm gonna make it a little bit longer because it should go all the way up to 0. So something like this. And then region 3, which is here around this part, I should have this one. Again, I'm gonna make it a little bit longer because it should touch all the way up to the dotted line. And then the last one, I should have this part here. This one. So this is the graph of my f of x. So which one out of 4 choices look the best? Well, I know I can eliminate A. C doesn't look right too because look at this one. It's going up there and then down, and this is, we are having totally opposite part here. And then it's between B and D. And I see that B is the well-matched one. So B will be my final answer. Okay. That's it for section 4.2. In next video, we are going to be doing whole process of graphing this. Okay.